So actually, this is a talk that it's a variant of a talk I gave at the beginning of the month at the Interspeech conference, which I didn't know would happen when Inya invited me to put this talk in the schedule. So it just happened this way. And it's about what I call an application of data management, that's how I see it, to the problem of speech recognition, and more generally to the problem of decoding any observed sequence of events so that it can be understood and the cause of that observation can be best explained, which is exactly what happens when somebody speaks and you have a device that recognizes what they have said. So the research that leads to this kind of solutions goes back to 1967 and to the Viterbi algorithm. So I can confidently say, without risking making any error, I can say that the foundation of this talk was part of the curriculum when you were studying, because 1967 is before DIKU was founded, which is 54 years ago. And you see that was a time when they didn't have laptops on their desks, they didn't have desktops either. But Andrew Viterbi was proficient enough to invent a dynamic programming algorithm which serves exactly the purpose of explaining the source of any signal or any observation. And that is still useful in many domains. It is even useful in speech recognition itself. For example, that's a recently published paper that verifies that. They use this algorithm, although there are also neural models for speech recognition, I should say. And it works based on a Markovian communication source where some events are happening and every event depends only on the previous one in that sequence, which is something that you can say that speech also corresponds to this kind of configuration. So it is a dynamic programming algorithm, which gives me a chance to take you back to your Introduction to Algorithms course some years ago. It goes through a recursive computation where it computes optimal solutions to a problem by relying on already computed optimal solutions to smaller versions of the same problem. And that's exactly what you need to do. So if you observe only one thing, if your sequence has only one vowel or phoneme, the only thing you need to do is to combine the prior probability that that thing can be heard to the probability that it can be emitted at any state of the possible states in which a speaker could be. And then you find the state that maximizes that thing, and that's your explanation. So that's what you do for a sequence of length 1. But of course, for a longer sequence, as the case is, that's not enough. You need to work recursively. So you find the highest probability that best explains how you arrived at a state I, or a phoneme I, at the observation of number j in a sequence of events, can be given as the best possible combination of some explanation that takes you to another state called k, which is a predecessor of your current state I, and you arrived there through the first j-1 observations. You see, one observation less, or reduced by one. And also you have to take into consideration that you have to move from state k to I, which is given by that coefficient over there, which is an element of a matrix that gives you this kind of transition probabilities. And you need to combine it with the probability of observing whatever you have observed at the state I in which you consider you will be. I hope this doesn't sound very confusing. This is just an application of dynamic programming. And so the main point is that you solve a problem by using solutions to small problems and expand them gradually to bigger ones. And the main point is that that's how the solution with parameters I and j depends on the list of solutions you have with parameters j-1 and some k, which are related to I. That's what you need to keep in mind. And so you have to run this algorithm. And unfortunately, it has a time complexity that is quadratic in the total number of states and linear in the number of observations, as this expression says. And even more worryingly, it needs memory that depends on the product of number of states times number of observations, which can be quite large, because we are talking about hundreds of thousands of states here and also observations in the order of some thousands, and when you multiply that by some bytes, you're already within the bounds of some memories. And so, okay, to give you, that is just a mathematical expression. to show you how this works in terms of implementation, you're going to have some loops, intermingled or nested loops, one over all observations, one over all states, and for each state, a loop over its neighbors. And then you're going to compute exactly what the previous equation said, that recursive equation that builds a solution moving one step forward. And let me visualize that a bit further. So the outer loop is about observations. And you will notice that whatever you do, the solution you build here depends only on solutions at the previous observation. Everything that comes before the previous is not used immediately. And we're going to come back to that. Keep that in mind. So here is what you do. You build your solutions at the first observation, and based on that, you do the second. Of course, that figure shows only 3 states. Think of something like 300,000. But so it keeps going, and eventually you have done the whole thing, and you are ready to give the answer to your problem. But now here is the catch. That equation is computing a maximum probability. What you really need is not the value of that maximum probability. Of course, it matters to be maximum. You want that. But what you really want is the sequence, the explanation, the whole path that gives you this maximum probability. So eventually you get the cell of that table that has that value, but you don't care about what that value is. You want to know how you came there. So you want to backtrack that path that brought you to that state through all the solutions you were building recursively all this time. And to get that path, you have to keep that blue thing in memory all the time because you want to backtrack through it. If you lose it, you cannot retrieve your solution. You don't have your explanation anymore. And of course, okay, you can try to cheat and you can say, okay, I will not keep that in memory. I will just drop whatever I don't need because, as I said, you only need the previous solution one step before to keep working. And then, you know, I will just keep dropping things, and then when I need them, I recompute what I have dropped. Well, unfortunately, if you do that, you just, you save a factor in terms of memory needs, but you create this factor in terms of time needs, time complexity. And that's also too bad because it means, you know, instead of waiting for 1 second, you wait for 10 seconds, for example. And that's not going to fly. So how can we do better? Can we preserve reasonable time needs and reduce the memory to make that work in any kind of small memory device? Unfortunately, space is quite cruel. Space, in the sense of memory, doesn't behave very well in the sense that, you know, if you have a time problem, you just wait a bit longer. But with space, you have to buy more memory. You cannot just wait. However, we can solve this problem by a technique. Let me take you back to your algorithms class some years ago. You can do divide and conquer on top of that solution that does dynamic programming. So you can split the problem in 2 halves, not recomputing the whole problem all the way to the end, as I was saying before, which is a naive solution. You have to somehow break this problem in the middle, remember how you have broken it, and recreate the solutions. And then you will ask me, okay, but how am I going to do that? What's the way of breaking this thing in the middle? Well, actually, the same dynamic programming we're already doing can keep track of where the middle of a solution is, if we just, of course, instruct you to do it this way. And if we succeed doing that, we will be able to retrieve 2 halves of the problem and solve those instead. And then you may be wondering, okay, and if I do that, how do I gain? Why is that a better thing than just the naive thing you proposed before? How does that save time? Well, it saves time for the following excellent reason. Remember, the time complexity has this expression. So that's the cost of solving your problem once. If you have to solve 2 half problems, you have to pay this cost for those halves. And if you have managed to break these 2 halves in a way that each one has at most half of the states of that whole model on which you are working, you're going to pay the square of half of k times t 2 times, which is exactly that expression. And then you're going to pay 4 times k squared over 16 and so on. And let me remind you that this is a thing called the geometric sequence, which actually adds up to nothing more than 2 times what you started with. And let me also remind you that in complexity analysis, if something is 2 times what we started with, it is just the same as what we started with. A complex factor doesn't matter. So yeah, actually, in practice, that is going to have a runtime overhead, but that is going to be very small and asymptotical, as we say, it won't matter. And okay, let me visualize how this happens. Let's say that's the hidden Markov model on which we are working to solve your problem. So you're finding a path through this that gives you the best explanation. And if this path has a middle place like that, which, provided that this model has no cycles, this can perfectly break everything into two halves that are no more than half of the initial, like the red and the blue part, and then you redo your solution over these two halves. And everything works as I said before. And you can do some pre-processing that will help you identify what are the right places to use, like this purple edge over here for breaking everything in middle. And yeah, so all that will happen through the recursion, and it will work fine. And so that is an algorithm we have already developed in the past. And then we brought that to a ready-to-use implementation by using a technique called beam search. Well, something I didn't mention previously is that if you want to compute all solutions, as I was saying, it's going to cost a lot also just because there are too many. So what people do in practice, in speech recognition applications, they don't preserve the full, vector of solutions. They keep the best solutions in every step, which doesn't guarantee you have the best solution at the end, but in practice, for a real-world application, it's as good as, almost as good as, doing all of them. So instead of having the full array of K, you have just a smaller number of B, and B is the size of your beam. So we can actually do that, and while doing that, we can even extend to use that in every graph that may also have cycles in the network, and it won't matter either, and it will also be quite practical, and we call that the middle path version. And so, yeah, we adapt a beam search middle path version of our solution. And implementation-wise, that also works quite conveniently. You have to, in terms of keeping the middle state, you have to keep track of what states were active in your beam at that middle state, but that is also something that can be easily done. So eventually, we arrive at this place. We started with an algorithm proposed more than 50 years ago that had these complexity characteristics. And eventually, we have an efficient, time-efficient and space-efficient formulation that eliminates one factor from space complexity, which is like dropping your memory needs from gigabytes to a few megabytes or even less. And time-wise, it is burdened only with an extra logarithmic factor. And let me show you what that means in practice in terms of measurements. Here is the time for running your speech recognition application. And the yellow line is actually, the purple line is the conventional solution that would already use beam search, so which is already time efficient, whereas the red line is what we do. The important thing to note is that the red line is following the purple line, and the difference is, less than seconds. And here, if you use a beam size in the order of 1,000, you also achieve practically zero error in the quality of your result. Whereas your memory is, as we see on the right side, our memory is the red line, which is more than 3 orders of magnitude less than the memory used conventionally. So that's why I say from gigabytes to megabytes and less. So that's all I wanted to say. I want to thank my co-authors, and thank you for listening.